All right, so yesterday we talked about a ton of different forces. All right, so we talked about a gravitational force, how that's always there. All right, so that symbol that we give to that is F sub G. We talked about normal forces, that force is going to be F sub N. We talked about applied forces, that will be F sub APP. We talked about frictional forces, that'll be F sub F. We talked about tension forces, that will be F sub T. We talked about air resistance, all right, that will be F sub air. I think that's relatively it. All right, we also talked about spring forces and elastic forces. All right, those are going to be interchangeable. All right, but those are different from the first six because we actually just have to spell those out. All right, so F sub spring is spring force, and then F elastic is the elastic force. And those two are really interchangeable with each other. All right, so we learned about those yesterday, and I got you to do the concept builder recognizing forces because that concept builder just got you in the routine of thinking about the forces that were at work in different scenarios. All right, so these are the symbols that we use whenever we draw things called free body diagrams. Now, I do simplify free body diagrams into FBD. So if you see FBD, that just means free body diagrams. All right, so all a free body diagram is just a diagram that shows the forces that are working on an object. Forces that are working on an object. All right, now, this does not include forces that are working from within an object. So I know that sounds weird, but if you think about a car, all right, so say I slam on brakes in the car. I am not going to include an applied force of me stomping on the brakes. I'm not going to include a tension or spring force from the brakes and all of the interlocking wires or whatever that are happening in the car to actually bring the car to a stop. I am only looking at the forces that are working on the car itself. All right, so we draw these arrows that are the relative size and always in the direction that the forces are going. All right, these are the steps for drawing a free body diagram. Pause this video so you can look over those, and we are going to just jump right into examples. All right, so our first example is a book that is being pushed to the right across a table surface that has a constant velocity. And for both of these, I've asked you to neglect air resistance. All right, so one thing about free body diagrams is that you are going to show the object as either a box or a dot. It does not matter to me which one you use. All right, it just depends on your preference. I don't care. All right, so the book is being pushed. I'm just going to use a box for the book. It doesn't matter if you use a box or a dot. All right, now we know that gravity is always at work on everything. So you will always have a gravitational force pulling everything straight down. Now, it is on a table. All right, it is on the surface of a table. So that table is what is keeping that book from going down, 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 down from the force of gravity, right? So that table is applying a normal force going upwards. And because that book is not going up and down, up and down, up and down, we know that the normal force is balanced with the gravitational force. Well, in a free body diagram, we have to show that they are balanced. And we do that by drawing slashes on the arrows. Those two slashes tell us that gravity and normal are equal and opposite. All right, so those are the vertical forces that are at work on this book. But we also know that this book is being pushed to the right. Well, if it's pushed...
Redford Smith, please come to lower school carpool. Redford Smith, come to lower school carpool.
I love that for us. All right, so it is being pushed to the right. Well, we know if something is being pushed, that is an applied force. So push to the right means that we have a rightward applied force. Now, we know that it is sliding across the table surface. So if it's sliding on that surface, we know that there is friction. So friction, we talked about it yesterday. Friction is an oppositional force. All right, it's going to go in the opposite direction as the motion. So if the book is moving to the right, the frictional force is going to be to the left. All right, so friction is to the left. Now, this constant velocity that we see right here tells us that our forces are balanced. All right, so again, we have to use slashes and dashes to show our forces are balanced. Now, we're not going to just do one slash for these, because if I left it like this, all of them have one slash, and that tells me that all of them are equal to each other. And that's most of the time not the case. So we would differentiate by just using two slashes for the horizontal forces. All right, so going to our next one. A ball is dropped from rest from the top of a building. All right, so we have our ball that is going downwards. So it is falling down, which we know, we should remember that if something is falling down, then it is going to be speeding up as it falls down. All right, so as it falls down, we know that gravity is pulling it down. And because I have neglected, okay, thank you. All right, go tell her I said thank you. Thank you. I got it. All right, so we know that gravity is pulling it down. Now, we're not going to have tension pulling it down. We're not going to have an applied force pushing it down. All right, so we know that gravity is pulling it down. So the only other force that would be present would be air resistance. But I've told you to neglect air resistance for this. So this is your free body diagram for this scenario. Now, what if I told you to not neglect air resistance? All right, remember that air resistance is a type of friction, so it's going to be an oppositional force. So it's going to go in the opposite direction as the motion, so your air resistance will go up. But it's going to be speeding up as it goes down, so that tells us that our air resistance is just a little bitty force going up. All right, and so you would not use slashes and dashes for this because they are not balanced. All right, moving on. We have a falling skydiver. All right, so we know that everything that is falling is accelerating, it's speeding up as it goes down. Well, there is a point where something that is falling can reach something called its terminal velocity. That's its maximum velocity. It also tells us that it is a constant velocity. You need to know that terminal velocity means constant velocity. All right, it is a constant vertical velocity. So that tells us that our forces are balanced. So if we draw our skydiver, we know that gravity is pulling him or her down. And we know that as he or she is falling through the air, the only other force that could balance out gravity is air resistance. All right, so air resistance is opposing gravity, and because terminal velocity means constant velocity, we have to show that they are balanced by drawing those slashes. All right, so same skydiver. After he reaches terminal velocity, he opens up his parachute. All right, well, hopefully you have seen movies, or maybe you've even gone skydiving. I don't think that's the case. All right, but you've seen movies, and after they open up their parachute, the skydivers slow down. All right, so slowing down is a type of acceleration. And when we have acceleration, that tells us that our forces are unbalanced. They are not equal to each other. All right, so we have our skydiver. And then we know that gravity is still pulling our skydiver down. But whenever he or she opens up that parachute increases that air resistance a ton. All right, so that air resistance, that force of air resistance is going to be a lot larger than that force of gravity. So we want to show that air resistance is larger by drawing a longer arrow. All right, and we would not draw the slashes and the dashes because they are not balanced. All right, so moving on, we have an elevator that's held by a cable slows down. All right, slowing down is a type of acceleration, which means that we have unbalanced forces. So we have our elevator. All right, we know that gravity is pulling that elevator down, but instead of speeding up as it falls, it's slowing down. So there has to be a force that's working against gravity, and we know that force is coming from that cable. All right, so that cable is providing a tension force. And if the elevator is slowing down as it goes down instead of speeding up, we know that that tension force is much greater than that gravitational force. All right, next we have a car that is skidding to a stop. Skidding to a stop is just another way of saying that it is slowing down. Again, slowing down is a type of acceleration. So having a type of acceleration means that I do not have balanced forces. All right, so we draw our car. All right, again, a dot or a box, whichever one. Now, it did not say it in this example, but it is safe to infer that this car is traveling on some kind of surface. All right, so we know that gravity is pulling the car down, and we know that that car is not traveling down, 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 down. That surface, that road is providing a normal force, all right, pushing it back up. And we know because it's not traveling up and down that those forces are balanced. So we draw our slashes and our dashes. All right, now we know that the car is traveling to the right, but is anything pushing it to the right? Is there an applied force going to the right? Is anything pulling it? Is there a tension force pulling it to the right? No. All right, what made it go to the right is internal. And once again, our free body diagrams only show forces that are working on the object. All right, so there is no rightward force. All right, now what would be causing it to slow down? That would be friction. So if the car is traveling to the right, we have a frictional force that is going to the left. It's opposing the motion. All right, so it's that frictional force that is actually causing it to come to a stop. All right, so here you see an unbalanced force, which is exactly what we should see because slowing down is an example of acceleration. Now, our last one is a little bit different, but you are going to see a lot of these. We have a large crate that is slowly accelerating down a steep and rough inclined plane. All right, if you ever have a scenario where you have an object on an inclined plane, the first thing that I want you to draw is the inclined plane. All right, so after you draw the inclined plane, then you can draw your object. So we have our crate. We know that gravity is always going down. Gravity will never go at an angle. It's always pulling down. And we know that it's on a surface. So that surface is providing a normal force, pushing it back against gravity. All right, but in this case, our normal force is not coming from a level ground or a level table or any level surface. It's on an incline. So one thing that you need to remember is that normal forces are always going to be perpendicular to their surface. A normal force is always going to be perpendicular to the surface. All right, and this crate is going down this inclined plane. All right, so don't draw this green line. All right, this is just showing you the motion. It's sliding down the inclined plane. Now, is there anything that is pushing it or pulling it down the inclined plane? The answer is no. Gravity is what's causing it to go down the inclined plane. All right, so there is no force that's going down this way. You're not going to draw a force going down this way. All right, but that is the motion of the object. Well, we were told that it was a rough inclined plane. All right, so we know that that's going to be plenty of friction. So we have friction. Again, friction is an oppositional force, so it's going to oppose the motion. So if the box is moving down the inclined plane, our friction is going to go up the inclined plane. So our frictional force would go up the inclined plane. All right? So this is our free body diagram. Now, something that a lot of people will mess up on is that they will set these equal to each other. All right, so they will put slashes and dashes on these to say that these are equal and opposite or balanced, and you can't do that. All right, these are not on the same plane. All right, you can only do that if they're on the same plane, meaning you can only do that if they are, sorry, I just erased all of that. All right, you can only do that if they are both vertical or both horizontal. All right, so none of these are going to be equal to each other. All right, so we do have a little practice that we're going to do with this, but as always, if you have any questions, let me know.